Assalamu alaikum. This is lecture 6 of software requirement engineering, and in this lecture I am going to discuss about some of the requirement modeling techniques that are helpful in visually creating software requirement specifications. And these requirement specification visual modeling tools are listed as under. For example, we have use cases diagrams, data flow diagrams, swim lanes, state transitions, decision tables, event responses, and entity relationships specifications. These diagrams help each of aspect of software requirement specification to formalize the requirement in a proper and visual representation. As a wise man said that a picture is worth a thousand words. So you should be aware that visual requirement models can help you to identify missing, extraneous, and inconsistent requirements. So you should also be well aware about the capabilities of human short-term memory capacities. So if you're going to analyze a list of 1000 requirements for inconsistencies, duplications, and extraneous requirement checks, it is nearly impossible. For example, if you are reviewing some requirement document and by the time you reach the 15th requirement, you are likely to forgotten the first few requirements that you have read in the start. And in similar way, you are very unlikely to find all of the errors simply by reviewing a textual form of requirements. Therefore, you need a pictorial form of requirement which is worth 1000 words for one requirement graphical representation. So requirements are called the voice of the customer to the analysis team, and these are covered or depicted in the forms of models for inconsistencies check, completeness check, and evaluating any extra requirements. So by listening carefully to how customers present their requirements, the business analyst can pick out keywords that translate into specific model elements. So a requirement analyst may analyze the type of words that are nouns. For example, requirement engineer analyze the requirements gathered from the customers to find out about the people, organizations, software systems, and other data elements that are connected or interacting with the systems. And mostly these kinds of nouns are represented in form of data flow diagrams, use case diagrams, entity relation diagrams, and other forms of diagrams such as state transition diagram and swim lane diagrams. So if an analyst uh, gathers some form of verbs which describes actions, things a user or system can do, or events that can take place. So again, it represents a flow of data or swim lane diagram, and it can also be covered by the use cases, ERD, and different other diagrams. If there are some conditions in the requirements, these are mapped with the decision tree table and decision tree diagrams, or even by the activity diagrams. So you have to select the right representation for the elicitation of the requirements so that all the stakeholders agree to the specifications. So if you're going to represent a system external interfaces, the context diagram and the use case diagram are cardinal indicators to help you to identify objects outside the system that connect to it. The context diagram and the data flow diagram illustrate the system inputs and outputs at a high level of abstraction. So we have discussed about the external interfaces or system context diagram in the previous few lectures. So if you have to represent some business process flow, you can do it by using a data flow diagram that represents how business process handles the data at a high level of abstraction. Similarly, you can use a swim lane diagram that shows the roles that participate in executing the various steps in a business process flow. If you want to specify data definitions and data object relationships, the entity diagram shows the logical relationship between the data objects. Class diagrams can also be used to show the logical connections between object classes and data associated with them. So if you are more concerned about the states, you can use the state transition diagrams or state tables that represent a high abstraction view of the possible states of a system or object and the changes between the state that what can take place under what certain circumstances. You can also use function requirements that provide the details that describe exactly what user and the system behaviors lead to the status change in the state transition diagram. If you want to model the complex logic, you can use Decision tables or decision trees that shows the possible outcomes from a set of related decisions or conditions. Similarly, if you want to model the user interface, you can use the dialog map diagrams to display what the actual user wants in an interface. You can also use other forms of methods such as storyboard or detailed screen layouts to describe the prototypes to show exactly how display elements will look like. So let's move to the first diagram that is very much helpful and it is widely used in the software requirement specification documents, and you can say it is the core aspect of the requirement modeling in a visual form. And the use case diagram is a form of usage-centered perspective to the requirement illustration and modeling. That means it focuses on the user and the system, how the user is going to operate it. So use case approach works well with the business applications, websites, services that one system provides to another, and it also works well with the systems that let a user to control a piece of hardware. So use case diagrams provide a high level visual representation of user requirements. Use case diagram shift the perspective of the requirement development to discussing what the user need to accomplish, in contrast to the traditional illustration approach for asking users what they want the system to do. You are more focused about the achievement of the task by the users. So the objective is to describe all the tasks that a user will need to perform with the system. The stakeholders ensure that each use case lies within the defined project scope. So if you want to model some requirements in the use case diagram, you can use different elements. For example, the box frame is used to represent the system boundary. There are some arrows from each actor which is represented by a stick figure, and it connects to the use cases which are represented as ovals. So here is the example of a typical use case approach. A use case describes a sequence of interaction between a system and an external actor that results in the actor being able to achieve some outcome of value. So the naming of the use case is very critical to analyze. It is written in the form of a verb followed by an object. So for example, you can use a verb and an object form in this example of first chemical tracking system, that is request a chemical. So start with the verb and with an action or object. So you select strong descriptive names to make it evident from the name that the use case will deliver something valuable for some user. So you can go through the number of use cases in this example, and you can see all the examples match this naming convention, and all the examples describe a sequence of interaction between system and an external actor. So the fundamental part of the use case approach is an actor, that is a person or another software system or a hardware device that interacts with the system to achieve a useful goal. So there is an arrow from an actor to the use case to indicate that he is the primary actor for the use case. The primary actor initiates the use case and derives the main value from it. So on the other hand, if arrow goes from a use case to another actor who participates somehow in the successful execution of the use case, other software system offer serve as a secondary actors, contributing behind the scenes to use case execution. The training database is just such a secondary actor in the figure described in the next slide. So the system gets involved when a requester is requesting a hazardous chemical that requires the requester to have been trained in how to safely handle such dangerous materials. So another name for the actor is the user role, because the actors are the roles that the members of one or more user classes can perform with respect to the system. Again, if you look at the previous slide, for example, the chemical tracking system use case called the request chemical involves an actor named requester. There is no chemical tracking system user class named requester, so both chemist and the members of the chemical showroom staff may request the chemical, so members of the either user class may perform the requester role. So here is an example of the use case diagram for the chemical tracking system. So again, a use case is a discrete, stand-alone activity that an actor can perform to achieve some outcome of the value. So for example, we have a primary actor called a requester, and we have a use case called receive chemical. So as the naming convention applies, that it is followed, the verb is followed by a object. So it is discrete, it is stand-alone, that it can be achieved independently, and it describes some achievement from the system. So a single use case might encompass a number of similar tasks having common goal. So a use case is therefore a collection of related user scenarios, and a scenario is a specific instance of a use case. So you can go through this example to identify different use cases. The use case description is often followed by a proper format. Usually a use case has a unique identifier that typically identifies a use case. So a use case has a name that states the user task in the form of verb plus object. So remember to use to the point names, for example, place an order. Then there is a small textual description written in a natural language that describes what the use case achieves. There can be list of preconditions that must be satisfied before the use case can begin, and there can be post conditions that describe the state of the system of the use case is successfully completed. So a number of lists of steps that shows the sequence of dialogue steps or interaction between the actor and the system that leads to the precondition to the post condition. So here is a typical use case description for the chemical tracking system. As you can see, there's a use case ID, there's a use case name, and there is a small description, precondition, postcondition, the normal use case code, the alternative actions, exceptions, priority, etc., and some further information. You can go through these examples to understand the concept further. Let's talk about the preconditions and the postconditions. As I have specified earlier that the preconditions define prerequisites that must be met before the system can begin executing the use case. So these are conditions that must hold before starting the process of a use case. The system should be able to test all these preconditions to see if it's possible to proceed with the use case, and the preconditions could describe the system state for a use case. To withdraw cash from the automated teller machine, the ATM must contain money. So this is a precondition. So, but these preconditions do not describe the user's intent. For example, user can have the intent that I need money. So, on the other hand, post conditions describe the state of the system after the use case is executed. So, post conditions can describe something observable to the user. The system displayed an account balance or a message. A physical outcome such as an ATM dispensed money and printed a receipt, or an internal system state changes. For example, the account has been debited by the amount of the cash withdrawal plus any transaction fees. So there can be different flows in the use case referred as normal flows, alternate flows, and exceptions. So one scenario is identified as the normal course of events for the use case. For example, normal case for the use case request a chemical is to request a chemical that is available in the chemical stockroom. So one valid scenario within the use case are described as one alternate. So if there are more than one valid scenarios, then these are described as alternate flows or secondary scenarios. So alternate courses or result in successful task completion and satisfy the user's use case post condition. However, they represent variation in the specifics of the task or in the dialog sequence used to accomplish the task. The normal course can branch off into any alternate course at some decision point in the dialog sequence and rejoin again the normal case later. However, most use cases can be described in simple prose. A flowchart or a UML activity diagram is a useful way to visually represent the flow logic in a complex use case as shown in the next slide. So flowcharts and activity diagrams show the decision points and conditions that causes a branch from the main course into an alternate course. So along with the alternatives, there are some cases known as exceptions. Exceptions are conditions that prevent a task from succeeding. So one exception for the case request a chemical is not commercially available. So this is an exceptional scenario. So if you do not specify the exception handling during the elicitation, there are two possible outcomes. First, the developers will make their best guesses at how to deal with these exceptions. Secondly, there is no exception handling and system will fail when a user hits the error condition because no one thought about the exceptional case. Exceptions are sometimes regarded as a type of alternate course, but it's useful to separate them. So you don't necessarily implement every alternative course that you identify or a use case, and you might defer some for the later releases. However, you must implement the exceptions that can prevent the scenario that you do implement from succeeding. So here is an example of activity diagram illustrating the normal and alternative course of a use case. So this represents the normal flow, and here is an alternate flow where we described normal flow can be branched to an alternate flow which can again rejoin the normal flow at a later stage during the execution. So use cases also represent a different kind of relationships. So you show two types of relationships called extend and include between the use cases in the use case diagram. So for example, if an alternative course is itself a stand-alone use case, you can extend the normal course by inserting that separate use case into the normal flow. For example, the search vendor catalog use case extends the request a chemical use case. In addition, the chemical stock from staff use the standalone search vendor catalog use the use case by itself. So for example, if you request a chemical, you also search for the vendor catalog. So sometimes several use cases share common set of steps. To avoid duplicating these steps in each such use cases, define a separate use case that contains the shared functionality and indicate that the other user use case include that sub-use case. So this is analogous to the calling a common sub-function in a computer program. As an example, consider an accounting software package and two use cases are pay bill and reconcile credit card. So both of these use cases involve the user writing a check to make a payment. So you can create a separate use case called a write check that contains the common steps involved in writing the check. So two transactions use cases both include the write check use case as shown here. You can also use macro use cases for aligning preconditions and post conditions. In many systems, the user can chain together a sequence of use cases into macro use case that describes a larger task. So some use cases for commercial website might include search catalog, add an item to shopping cart, and pay for the items in the shopping cart. So if you can perform each of these activities independently, they are individual use cases. So you might also be able to perform all three tasks in a row as a single large use case called by product as shown in the slide. So to make this work, each use case must leave the system in a state that enables the user to complete the next use case immediately. So that is the post condition of the one use case must satisfy the precondition of the next use case in the sequence. As you can see, example is done here for the by product, and there are three different use cases such as search, catalog, add to shopping cart, and pay for items in the shopping cart. There are several ways to identify the use cases. So first of all, you have to identify the actors and then identify the business processes in which each actor participates. So you identify the external events to which the system must respond and then relate these events to the participating actors and specific use cases. So you express the business processes in terms of specific scenarios, generalize the scenarios into use cases, and identify the actors involved in each use case. Then you derive the use cases from existing functional requirements. So if some requirements do not trace to any use case, consider whether you really need them or you want to eliminate from your requirement specifications. Use case and function requirements go side by side, and software developers do not implement business requirements or use cases. They implement the functional requirements, which are specific bits of the system behavior that allow users to execute the use cases and achieve their goals. So use cases describe the system behavior for the actor's point of view, which omits a lot of details. As you can see in the previous slide, you simply placed a use case called request a chemical while hiding the underlying implementation details or the functional requirements. So a developer needs many other views to properly design and implement a system, and organizations get into trouble when they simply hand use case descriptions to developers for implementations. So for example, the user of an ATM does not care about any backend processing the ATM must perform, such as communicating with the bank's computer. This detail is invisible to the user, yet the developer needs to know about it. However, there are certain benefits of the use cases. For example, it is very easy to know about the system functions. Often it is frustrating and wasteful for the developer to write code that never gets used, and if you are able to discern the information that will be used or the actions that will be used by the user, developers are more likely to create a code that is beneficial for the user and the system. Use cases lead to the functional requirement that will allow the user to perform certain known tasks. Therefore, this helps prevent an orphan functionality that will never be used. So the use cases approach helps with the requirement prioritization as well. The highest priority functional requirements are those that originated in the top priority use cases. So a use case could have a high priority for several reasons. For example, it may describe one of the core business processes. It may describe many users who are frequently using it. It may describe a favored user class requesting it, or it provides a capability that is required by the regulatory compliance authority. So there are technical benefits of use cases as well. So the use case perspective reveals some of the important domain objects and their responsibilities to each other. Therefore, developers using object-oriented design methods can turn use cases into object models such as class and sequence diagrams. So you need to be very careful when designing the use cases. There are certain traps to avoid. And first is that you may get plugged into the large amount of use cases. So if you're caught in the use case explosion, you might not be writing them in an appropriate level of abstraction. So you do not need to create a separate use case for every possible scenario. Instead, you can include the normal course, alternative courses, and exceptions as scenario within the single use case. The another trap is inclusion of the user interfaces design in the use cases. So use cases should focus on what the user needs to accomplish within the system, not how the screen will look like. So you have to emphasize on the conceptual interactions between the actors in the system and differ use cases or user interfaces specific to the design stage. So you can also get into a trap of data definitions in the use cases, and use cases explorations naturally stimulate data discussions, which are thinking about what are the data elements that serves as an input and output during the interactions. You can also fall into the trap of highly complex use cases development. So you build the use cases at a considerable level of complexity, and if use case is involving too many alternate and exception flows, you can divide the use case into multiple use cases to decrease the complexity. So use cases that users don't understand is another problem, and if you write such cases, then the business processes or goals in those use cases, there will be a problem of the understanding. So you have to write these cases from the user's perspective and not from the system's point of view, and ask the users to review them, not the developers. Keep the use cases as simple as you can while still achieving the goal of clear and effective communication. The next graphical tool for requirement specification and modeling is the data flow diagram. And the data flow diagram is the basic tool of structured analysis. Data flow diagram identifies the transformational processes of the system, the collections of data or physical materials that the system manipulates, and the flow of data materials between the processes stored in outside the world. So data flow modeling takes a functional decomposition approach to system analysis, breaking complex problems into progressive levels of detail. This works well for transaction processing systems and other function-intensive applications. Through the addition of control flow elements, the data flow diagrams technique has been extended to permit the modeling of real-time systems. High-level data flow diagrams provide an holistic bird-eye view of the data and processing components in a multi-step activity, so which is very much similar to the context diagram which was described in few lectures earlier, and it represents the highest level of abstraction of data flow diagram. So you can elaborate the context diagram to number of levels such as level 1, level 2, and level 3 data flow diagram. So here is an example of data flow diagram. As you are well aware about the context diagram, that the context diagram shows the interaction of the system and components and the data flows between the components and between the internal system components and the external system. Similarly, you can use the context diagram to represent the flow of data in a top level data flow diagram. And the symbols represent the components are in circular form, and the data flows are represented in a horizontal form, and arrows show the flow of data direction. So the single circle that represents the entire chemical tracking system is on the context diagram, and it has been subdivided into 6 major processes or bubbles. The external entities are shown in the rectangles. So all data flow from context diagram also appear in the level 1 data flow diagram. In addition to level 1 diagram contains several data stores depicted as a pairs of parallel horizontal lines which are internal to the system and therefore do not appear on the context diagram. Similarly, a flow from the bubble to a store indicates that the data is being placed into a store, or if the direction is reversed, then the process specifies the reading of data. So the business analyst continues this progressive refinement until the lowest level diagram containing only small processes operations that can be clearly represented in a narrative text, pseudocode, swim lane diagram, or an activity diagram. So on each level of data flow diagram must be balanced and consistent with the level above so that all the inputs and output flows in the child programs or diagrams match with the flows in its parent level. So processes communicate through data stores, not by direct flows from one process to another. Similarly, data flow cannot directly from one store to another or by directly between external entities or data stores. So you should not attempt to employ the processing sequence using the data flow diagram, and the data flow diagrams only show the flow of the data between the components. So you should name each process as concise action, verb plus object such as generate reports. The number of the process using the level of the diagram, for example, level 0, level 1, level 2 diagrams. So don't show more than 8 to 10 processes in the single diagram, otherwise it will be difficult to draw, change and understand. So if you have more processes, you can add another layer of abstraction in grouping related process to a one higher level process. The processing that a DFD bubble represents normally requires both input and output flows. Another form of visual representation of requirement is the swim lane diagram, which provides a way to represent the steps involved in a business process or operations of a proposed software system. They are the variations of flowcharts subdivided into visual subcomponents called lanes. These lanes represent different systems or actors that execute the steps in the processes. Swimlane diagrams are most commonly used to show business processes, workflows, or systems and user interactions. These diagrams are sometimes called cross-functional diagrams. Swim lane diagrams can show what happens inside the process bubble from the data flow diagram. They can also be used to perform detailed analysis to identify the requirements that support each process step. So here is an example of swim lane diagrams in which you have identified different actors, cameras, buyers, receiving, and vendors. Swim lane diagrams can contain additional shapes, but most commonly used are described as under. So first is the process steps, which are shown as rectangles, for example, creating a chemical or receiving the chemical in the laboratory. Then there is transitions between process steps shown as arrows, as you can see here or here. Then there are decisions shown as diamonds. If there is a condition, then you have to follow certain paths. Swim lanes are used to subdivide the processes as shown in the horizontal level. So the swim lane described in the previous slide shows roles or departments and showing which group execute each step in the business process or to order chemicals from the vendor. So you can identify the function requirements. You can start from the first box called creating a chemical request and think about what functionality the system must have to support this step as well as the data requirement for the chemical request. So at the later stage, you can receive and approve invoice and it might trigger the team to lead to identify requirements for what it means to process an invoice. State transition diagrams and state tables are two state models that provide a concise, complete, and unambiguous way to represent the state of an object or a system. It shows the possible transitions between the states visually, and it can be represented using a unified modeling language. So it specifies the states an object goes through during its lifetime. So it can have three types of elements represented as states, state changes, transitions, and events or conditions. States shown as rectangles, some notations use circles as well. So transitions shown as arrows which connect pairs of rectangles or circles. Events cause or event or conditions that cause each transition to take place shown as a text label. So here is an example of state transition diagram. This represents the state of the object or the system. This represents the transition in the form of arrow, and this represents the condition in the form of text. Another way to represent states of the object or a system is by using state table, which shows all the possible transitions between states in the form of a matrix. So a business analyst can use the state table to ensure that all transitions are identified by analyzing every cell in the matrix. So all states are written down in the first column and repeated across the first row of the table, and the cells indicate whether the transition from the state from the left to a state at the top is valid and identified the transition event to move between states. So these two diagrams show exactly the same information, but table format helps to ensure that no transitions are missed, and the diagram format helps the stakeholders to visualize the possible sequence of transitions. So here is an example of state table. As you can see, requirements are listed in the first column and first row to check the transitions against each state. So as in the in preparation state, a user can move to two other states. Similarly, if you are in the postpone state, you can only start the preparation of the document. Our software system is often governed by the complex logic with various combinations of conditions leading to different system behaviors. For example, if the driver presses the accelerate button on a car cruise control system, then the car is currently cruising. The system increases the car speed, but if car is not cruising, the input is ignored. Developers need functional requirements that describe what the system should do under possible combinations of conditions. It is easy to overlook a condition which results in a missing requirement. These gaps are hard to spot by reviewing the textual specifications. Therefore, decision tables and decision trees are two alternative techniques for representing what the system should do when complex logic and decisions come into play. So a decision table lists the various values for all the factors that influence the behavior and indicates the expected system action in response to each combination of factors. These factors can be shown either as statements with the possible conditions of true and false, as questions with the possible answers of yes and no, or as questions with more than two possible values. So this figure shows the decision table for the logic that governs whether the chemical treating system should be accept or reject each request for a new chemical. And four factors influence this decision. First of all, you have to check whether the system user who is making the request is authorized to request chemical. Secondly, check the chemical is available either in the chemical stockroom or from a vendor. Thirdly, check whether the chemical is hazardous chemical that requires special training in safe handling. Finally, check whether the user is creating the request is trained in handling this type of hazardous chemical. Similarly, this figure shows the same information about the chemical tracking system acceptance in form of decision trees. The five boxes indicate the five possible outcomes of either accepting or rejecting the chemical, and both decision tables and decision trees are useful to document requirements to avoid overlooking any combinational conditions. So even a complex decision table or tree is easier to read than a mass of repetitious textual requirements. In some cases, you also might require to capture event and their responses. And in applications such as batch processes, computationally intensive systems, which have just a few simple use cases, you can use event response tables. The complexity of these applications lies in the computation performed or in the reports generated, not in the user-system interaction. So a requirement technique often is used for real-time systems is to list the external events to which the system must react and corresponding system responses and to identify the external events to which the system must respond. So an event is some change or an activity that takes place in the user requirement that stimulates a response from the software system. An event response table, also called the event table or event list, itemizes all such events and the behaviors the system is expected to exhibit in a reaction to each event. So there are three classes of system events: business event, signal events, and temporal events. Business events are the events that are generated by a human user that stimulates a dialogue with the software or as when the user initiates a use case. The event response sequences correspond to the steps in the use case or Swimlane diagram. If the event is a signal event, that is registered when the system receives the control signal that a reading or interrupt from the external hardware device or another software system. For example, when a switch closes, a voltage changes, another application requests a service, the user swipes his finger on a tablet screen. The other form of a table is temporal event, and a temporal event is time triggered as when the computer's clock reaches a specified time, say to launch an automatic data export operation at midnight, or when a preset duration has passed since a previous event, for example adding a system that logs the temperature read by a sensor every 10 seconds. So here is an example of event response diagram or table which identifies the different types of events such as business, temporal, and the signal events and their relevant properties. So as specified earlier, event analysis works especially when for specifying real-time control systems, and to identify events, consider all the states associated with the events you are analyzing and identify any events that might transition in the object into those places. So you review the context diagrams for any external entities that might initiate an action or trigger an event or require an automatic response. table contains a sample event response table that partially describes the behavior of an automobile's windshield wiper. The table is depicted in the next slide. So other than event 6, which is temporal event, these are all signal events. The response could simply alter some internal system information, or it could result in an external visible result. So here is an example of event response table, and the event is specified as setting wiper control to low speed. So you generate a system state that turns the wiper off on a high speed and turns the wiper on intermittent speed. The system response should be the setting of wiper motor to a low speed. Similarly, there are other system responses and system states. So you can also model data relationships in form of visual diagrams to elicit the requirements, and which are very much similar to the representation of data flows using the data flow diagram. However, in the data relationship diagrams, the data model depicts the system's data relationships instead of processes. And a commonly used data model is the entity relationship diagram, or in short ERD. And if your ERD represents a logical group of information from the problem domain and their connections between them, you are using the ERD as a requirement analysis tool. And an analysis of ERD helps you to understand and communicate the data components of the business of the system without implying that the product will necessarily even include a database. So when you create an ERD during the design, you are defining the logical or physical implementation structure of the system database. That implementation view extends or completes the understanding of the system begun during the analysis and optimizes its realization in, say, a relational database environment. So here is an example of entity relationship diagram for the same chemical tracking system. And again, there are some entities and there are relationships between entities specified in the form of diamonds. So entities could represent physical items, for example, people, or aggregations of data that are important to business you are analyzing, or to the systems intended to build. Entities are named as singular nouns, and these are shown in rectangles. So figure in the previous slide illustrates a portion of entity relationship diagram for chemical tracking system using the Peter-Chen notation, which is one of several common ERD modeling notations. You can notice that the entities named chemical request, model catalog, chemical stockroom inventory appeared as the data stores in the data flow diagram. So other entities represent actors who interact with the systems, for example, requesters, which is the physical items that are part of the physical operations, chemical containers, and blocks of data that were not showed in the DFT level 0, but that would appear in the low level DFT, for example, container history or chemical. So during the physical database design of relational database entities, normally it transforms into form of tables. So this concludes the discussion of today's lecture, and in this lecture we discussed different form of requirement specification techniques, and requirements are better specified and visualized in form of graphical elements, and we discussed several graphical techniques that help to analyze and check the completeness of the requirement specifications. So if you are interested to read more about the topic, you can go through the chapter 8 and chapter 12 of the recommended book. If you have any question, you can ask me. Thank you very much.